Okay, so in this next section, what we need to do is take a look at how then do we add vectors together as components. And what we're going to see is that we have to take them apart. We have to decompose them into their y component and their x component, their vertical and their horizontal, their sine, their cosine. And so one method of adding vectors makes use of something called the projection of a vector along the axis of a rectangular coordinate system. Okay, so we can see that here. We've got in essence, we've got a vector here. It could be a resultant vector that's going off at, something along the lines of 45 degrees, and it has some magnitude. But you can see if we trace down this dotted line onto the x line, we've got one component that we call a sub x, and if we trace across here, we have another component we call a sub y. So these projections then are called the components of the vector. Any vector can be completely described by its components. A vector A can be expressed then as the sum of its two vectors, a sub x parallel to the x-axis and a sub y parallel to the y-axis. So that our original resultant, if you will, A, is equal to the vector sum, not the arithmetic sum, the vector sum of component a sub x plus component a sub y. Any vector A lying in the xy plane then can be represented by its rectangular components a sub x and a sub y. The components then form two sides of a right triangle, and we will be interested only in right triangle trigonometry in this course. Okay, so we're going to look at how do we use the right triangle trigonometry to do vectors, the hypotenuse of which has the magnitude a. So a here becomes the hypotenuse of the triangle. If we look at from 0 to this point here on a sub x, up to the height of a sub y and back to 0 along the hypotenuse, there is our right triangle, because right here we have a 90-degree angle, so that makes it a right triangle. Thus it follows that A's magnitude and direction are related to its components through the Pythagorean Theorem and the definition of the tangent. So we've got to rely on some mathematical relationships here. First, let's look at the Pythagorean Theorem. The hypotenuse is equal to the square root of the sum of a sub y squared plus a sub x squared. So when we take the length of a sub y and square it, if we take the length of a sub x and square it, add the two together and take the square root, what we will end up with is the magnitude of a, the length of this vector from 0 out to this point in space. To now determine the angle associated with that hypotenuse or that resultant vector, what we do is we rely on the trigonometric identity that says that the tangent of theta, there's angle theta right here, is equal to the quotient y over x, a sub y component, a sub x component. And then what we need to do is solve for the angle theta. So if we take the inverse tangent of both sides of the relationship here, when I take the inverse tangent of theta, I get theta. When I take the inverse tangent of a sub y over a sub x, I get inverse tangent, tan to the minus 1, multiplied times the quotient, a sub y over a sub x. So these relationships here are going to be the first mathematical relationships that we need to make sure we get down. If you're keeping a loose leaf binder or a spiral binder and making notes to yourself as you go, I would sketch this diagram and write these relationships for future use, because you're going to use it a lot. Also, from the definitions of the sine and the cosine of the angle, we can see that by definition, the cosine of theta is equal to the side a sub x over a, the hypotenuse, and the sine theta a sub y over a. Some of you may remember the mnemonic SOHCAHTOA. So TOA is sine, cosine, and tangent. The cosine of theta is equal to the side adjacent divided by the hypotenuse. The sine of theta is the side opposite by the hypotenuse, and the tangent is the side opposite over the side adjacent, okay? And it's formed by this triangular relationship that we see on the bottom. So what we can do then is, if we want to solve for a sub x, in this case here is our a sub x, all I have to do is take a, multiply it by both sides, so I get a sub x is equal to the magnitude of a times the cosine of theta. And I do the same thing, a sub y is equal to a times the sine of theta. So any vector a lying on the xy plane can be represented by those components, and that's how we get the numerical value of a sub x and a sub y, so that we can determine what that component is, a sub x, and what that component is, a sub y. Because what we're going to be doing is adding these vector components together, all the y components, all the x components, and then we're going to put them back together using the Pythagorean Theorem and the inverse tangent of theta, and come up with a hypotenuse or a resultant for our solutions. It may be more convenient to express the components of a vector in a coordinate system having axes that are not horizontal or vertical, but are still perpendicular to each other. So you can see what we've done here is we've taken our original relationship and we've tilted it up off of the x-axis. Sometimes this just makes the math easier. So the rectangular components then of B along the axis then are given by what we've done here in this rotation. So you notice we have B x prime is equal to B cosine theta prime, and the same thing for by. That should be by prime right there. Okay, and the same thing for tangent theta prime. Okay, so all the math remains the same. You just have a rotated amount here that you would have to deal with. So in solving for problems that look like this, the problem-solving strategy for adding vectors together is when two or more vectors are to be added, the following steps are used. First, select a coordinate system. Sometimes it's easy to start with rectangular or Cartesian and then move to polar or vice versa. Draw a sketch of the vectors to be added or subtracted and label each vector, okay? Then find the x and y components, a sub x, a sub y components then of all of the vectors. Find then the resulting components, the algebraic sum of the components, okay, that's the vector sum in both x and y. Then use the Pythagorean theorem to find the magnitude of the resultant vector. Use a suitable trigonometric function to find the angle the resultant vector makes with the x-axis. So let's look at an example here. This problem says find the horizontal and the vertical components of the 100-meter displacement of a superhero, like Superman, flies from the top of a building along the path shown. So if you can imagine here, this A is the path shown, and these are the vector components that we're going to deal with. So the triangle formed by the displacement and its components is shown in the diagram. Because A is 100 meters, so that's from 0 out to this point in space, and it forms an angle of 30 degrees or minus 30 degrees from the horizon or the horizontal. Theta is negative because it's measured clockwise from the x-axis. So if we look at the component a sub y is equal to a times the sine of theta. So a is 100 meters. The sine of minus 30 degrees gives me a component value for a sub y of minus 50 meters. Note that the sine of the negative angle theta is the same as the negative sine of theta, okay? Some trigonometry. If you've had some trigonometry in the past, you know that the identities tell you that that's true. The negative sign for a sub y reflects the fact that displacement in the y direction is downward from the origin. Okay, so the angle is telling you that. Now we look at the component of the x-axis, so the x component. A sub x, again, a cosine theta, with that same 100 meters for a, cosine of minus 30 degrees. Now this gives me a magnitude of positive 86.6. Note that cosine of negative theta also equals minus cosine of theta. Also from inspection of the diagram, you should be able to see that. So all we've done is we've taken the displacement, 100 meters, and the fact that we had a 30-degree angle from the horizon or the horizontal, and calculated for our two components, a sub x and a sub y. Okay? Let's see if I can fix that. There we go. That's better. Okay. So when we come back, we're going to take a look at displacement. We learned a little bit about displacement in our previous chapter, but we're going to look at it now in terms of a polar relationship.